Hello students, and welcome to our first video for this week about Chapter 7, Substitution and Elimination Reactions. Now this is a very foundational chapter. It's going to be very important to understanding the rest of the chapters that come afterwards. It's our first chapter about reactions. As we move forward, most of the chapters will be focusing on reactions associated with a particular functional group. But many of the trends and the patterns that you see in the mechanisms for all of these reactions will involve parts that include substitution. And so you'll want to focus very much on this chapter and make sure that you learn it very well so that you can have success in Chem 212 and Chem 213. So in this chapter, we're going to be focusing on reactant molecules that are alkyl halides. And so those are ones that have halogen atoms attached to carbons here. Notice that fluorine is not included. Fluorine, as it turns out, will not be great for this purpose. You can think about it in terms of the last chapter. A fluorine-carbon bond is the shortest of all these bonds to the halogens because fluorine is very small at the top right of the periodic table. So its bond is very strong. It's hard to break. Because it's so short generally, and so that's why it's not as good as of a reagent as alkyl halide is a chloride, a bromide, or an iodide. The hybridization of the carbon atom and its geometry will matter. The reaction will proceed in a different way often if it's sp3 hybridized versus if it's sp2 hybridized, and so that's something we'll have to think about as well. sp2 hybridized, it's trigonal planar, which is a different shape than if it's sp3 hybridized and tetrahedral. There are two reactions that alkyl halides commonly undergo. They are substitution, in which we have a halogen atom, and this is reacting with a so-called nucleophile. We talked about nucleophiles in the last chapter. Nucleophiles are Lewis bases. They donate their pair of electrons in order to make a bond. And so when the halide leaves here, it leaves as a halide ion. It keeps the two electrons in the bond with it, the red ones here. And the nucleophile then uses its two electrons to bond to the carbon. In an elimination, we have a base instead. And so here we're going to talk about the qualities of nucleophiles and bases. But bases accept protons. And so at least the Bronsted-Lowry definition, they accept protons, and that's exactly what happens here. A hydrogen atom is removed from a carbon here, and then the halogen atom also leaves and ultimately then get a pi bond between two of the carbon atoms, double bond. That is referred to. So nucleophiles and bases have in common that they want to donate lone pairs. For some bases, they want to grab protons more than others. So those other ones that don't grab protons as much end up being called weak bases, but can still be strong nucleophiles if they do have electrons that they can donate to a bond. So because these reactions either of them can occur with the reaction of a base or a nucleophile, which sometimes overlap in their properties, their chemical properties, these reactions will be in competition with one another. Later on in the chapter, we'll try to evaluate which of these reactions is likely to occur. So here we can see that the reactant is hydroxide. There's also sodium, but it's a spectator ion. And so the hydroxide is considered both a strong base and a strong nucleophile. And so it can accept this proton, let's say from this carbon, accept a hydrogen, then the chlorine leaves and we can get the elimination product. Or the OH can replace the chlorine atom and we can get the substitution product. In the case of a strong base, strong nucleophile, we'll find later that the elimination product is a major product, although some of the substitution product is also produced. In terms of the word substrate, that's a word we're going to be using a lot. You can see there are two reactants in this reaction. There's the alkyl halide and there's the hydroxide, the nucleophile. We wrote the hydroxide above the line. We generally call one of the reactants, we often call it the reagent, while the other one's called the substrate. So here, the 2-chloropropane is the substrate, and we write the substrate before the arrow. And oftentimes we write the reagent or the other reactant above the arrow. So that's a little bit of different notation that you might be used to, but it's going to become very common as we move forward. Now, why alkyl halides? The reason is because halogen atoms are polar, and so they pull electrons towards themselves and they become partially negative, causing the carbon that they are attached to lack electron density and become partially positive. And therefore, it's an electrophile. It will attract electrons, and so the negative nucleophile will be attracted to the positive carbon area and will attempt to make a bond. The halogen in these contexts is called a leaving group, and we'll have ways of evaluating the various chemical properties of the nucleophile, the substrate here, which is the alkyl halide in this case, and the leaving group, and also the solvent. And depending on all those factors, differing reactions. So in terms of evaluating leaving groups, a good leaving group is one that can stabilize the negative charge well, which is exactly the same property we use to describe a good conjugate base of a strong acid. And so we can evaluate this based on REO. And so, for example, if we're looking at iodine in terms of a atom, it's an electronegative atom. It's also very large. Remember, when we're considering atom and REO, as we go down the periodic table, the atoms get larger, and that helps them to better stabilize the negative charge. So you can see iodide does that best, followed by bromide and chloride. And then we had the conjugate base of sulfuric acid, the bisulfite ion, even better at stabilizing a negative charge. That is this so-called sulfonate. We'll talk about those as well. This has extreme resonance here due to the fact that we have a allyl lone pair, and that also contains resonance throughout this whole aromatic ring as well. Oxygen itself can stabilize the negative charge pretty well in terms of atom of REO. Fluoride less so because of its small size. And then you have the alkoxide ions, and finally those are worse and worse conjugate bases. Although they have the oxygen atom, that's about all they have going for them. Finally, amide is a terrible leaving group. It's a great base, very, very unstable. It wants to grab a proton badly. So we can go back to REO from previous chapters and use that to evaluate the quality of the leaving group. The leaving group 1, that is a great conjugate base. Same properties. The great conjugate base can stabilize the negative. So alkyl halides are compounds where carbon is attached to a halogen. And so we've talked about how to name these. I'll just briefly review it since we're going to be seeing them so much today. We do the same things we talked about in Chapter 4. We identify the name of the parent chain. We identify the substituents. We assign a locate number such that it will be lowest for the first substituent, or tied than the second, and so forth. And then we assemble the name alphabetically based on writing the various substituents in their order relative to the alphabet, their first letter. So here we're going to be looking at halides. So here, for example, the parent chain is propane with 1, 2, 3 carbons, and the chlorine is on the second carbon, so we call it 2-chloropropane. All the halides they have chloro, iodo, bromo, fluoro, so on. Here we have a parent chain that is pentane, 1, 2, 3, 4, 5 carbons. We number left to right because that's closest to the first branches here. So carbon number 2 has a bromo group. It also has a methyl group. We put the bromo before the methyl because B comes before M in the alphabet. In addition, we can have stereoisomerism. And so if we have a chiral carbon, for example, the 5th carbon here is chiral, we're going to have to determine if it's R or S, and we'll put that at the beginning of the name in parentheses. And so in this case, the highest priority group, the lowest priority group will be the hydrogen. Whoops, that's a dash. The hydrogen dash right here. So that's priority 4. The bromine will be priority 1. This will be priority 2. This side will be priority 3, using the same ways that we used in chapter 5. And so we are this one because although they're tied here, when you go here, you have CCC, beats right here the HA. Why this one's we have R, and then that's 5-bromo, 2,3,3, 2,3,3 trimethyl heptane. And so nothing real new in terms of nomenclature here. We've discussed this previously. One thing that we hadn't discussed, though, is that when it comes to small alkyl halides, the common names are extremely common. You'll even see them in bottles in the lab. So, for example, instead of seeing a bottle that says dichloromethane, which would be the IUPAC way of naming it, you'll see in a lab in the bottle methylene chloride sometimes, or in your lab manual. Some of these common names, like methylene chloride, are just so ingrained in language of chemistry, just the common language of chemistry, that even though the IUPAC naming system is better, they still persist in people's normal language. For example, here, this would be chloroethane. According to the IUPAC, a lot of people call it ethyl chloride. So watch out for common names when it comes to alkyl halides. They are very common. They're not the preferred way. So if we were giving reasonable names for the following, let's do one of these here. So here, if we're giving reasonable names to the guy on the left here, it's got, the parent chain is going to have 4 carbons. So it will be this right here, say, parent chain. So we're going to end the name with butane. And now we've got on one carbon here, we have a methyl. Here we have a bromo and iodo. These are both on the second carbon, but the second group, iodo, would also be on the second carbon if we number from right to left. So we're going to number 1, 2, 3, 4. Okay. And then we do have a chiral carbon right here. This one is attached to 4 different groups. And so we're going to have to prioritize those. So let's do that. In terms of priorities, the iodine will have the highest priority, having the highest atomic number. Bromine will be second. And then this carbon here is attached to 2 other carbons, so it's CCH. And this carbon here is attached to 3 hydrogens. So the carbon beats the hydrogen. And so this is going to be number 3 in this direction, and this one will be 4. Now we don't have number 4 on the dash, so we'd have to redraw this. Redraw it. Wedge, dash. Our numbers are 1, 4, and 3. We're going to do a double switch here. So I'm going to switch. Now here we need the 4 to get on the dash. So I'm going to switch the 4 into 2. And I'm going to switch the 1 and the 3 to make this happen. And so, okay. And so we switch our numbers here. And now the 1 is going to be on the line. The 3 is going to be wedge. 4 is going to be dash. And 2 is going to be line, and we have 1, 2, 3, a counterclockwise left hand S. So this is going to be S at that carbon. So now we're ready to write the name. So in terms of the groups, we have 3 different substituents here. We have a methyl, we have a bromo, and we have an iodo. Methyl is going to go last because M comes last in the alphabet. So we're going to say methyl butane, and methyl is going to be on the 3rd carbon. 3-methyl butane. And then we're going to put iodo next, iodo, and that is going to be on carbon number 2. Then we also have bromo, also on carbon number 2, bromo. And then finally, we need to say whether it's R or S on carbon number 2. And since there's only one chiral center, we don't need to say 2R. It's okay to say R. So R, 2-bromo, 2-iodo, 3-methyl butane. Butane because the parent chain has 4 carbons. Methyl, we're going to number right to left because the second carbon here has 2 groups. Methyl is on carbon number 3, iodo and bromo on carbon number 2, and that carbon number R, we could say 2R or just R. So you can try some more examples also. Part of the home. So often when we're thinking about where a reaction will occur, we want to refer to the carbons that a particular group is attached to. Often we'll use this naming convention where we call the alpha carbon the carbon that our group of interest is directly attached to. We'll call the beta carbon which is one space away, and the gamma carbon, which is 2 spaces. And so what's going to really matter here is the number of carbons that the alpha carbon is attached to. And we have a kind of nomenclature for that. So here the alpha carbon is this one right here, here, and it has 1 carbon attached. We would call that primary. Here, this alpha carbon has 2 carbons attached. Our group representing any group that contains a carbon atom at that spot. So that's going to be called secondary. And if the alpha carbon has 3 carbons attached, we're going to call that tertiary. And that's going to greatly affect the way in which the reaction will occur and the mechanism that it will undergo. There's lots of alkyl halides around. They can be used as insecticides. They're used as refrigerants. These alkyl halides are common everywhere. And so if we're looking for alpha or beta carbons here, so this would be an alpha carbon attached to a halogen. This would be beta 1, gamma. Here, gamma. Here, this would be alpha carbon, beta carbon, gamma carbon, alpha. Well, alpha. Their particular. Yeah, so besides insecticides, they're in dyes. You'll find them in drugs. For example, sucralose, or Splenda, the sweetener, has lots of carbon-chlorine bonds. And lots of other alkyl halides are quite common. So now let's talk about the reactions in which that they will undergo. So we're going to talk about substitution first. So a substitution reaction involves the loss of the leaving group or the halogen and a nucleophilic attack. And these steps can occur either at the same time, which we call concerted, or stepwise, one step and then the other. So we talked about mechanism and arrows for nucleophilic attacks in chapter 6. And we also mentioned this briefly. The nucleophile attacks the electrophilic carbon, which is the one that is attached to the halogen atom, which is pulling electron density away from it. And then the halide leaves by taking both electrons with it, leaving a halide ion. And these 2 steps can occur simultaneously or one after another. Nucleophilic attack, loss of the leaving group. Those are 2 of the patterns we learned in the last chapter regarding reaction mechanism. So in a stepwise mechanism, in the stepwise mechanism, the leaving group leaves first. And so here we have an arrow representing the loss of the halide, so it takes the 2 electrons with it, so it has a negative formal charge. And then we have a carbon with 3 bonds and no lone pairs, so it's got a positive formal charge. After that, the positive formal charge carbon is very attracted to the nucleophile, negative, or at least has electrons, if not negative. And so those electrons can attack and create a bond. So we have loss of leaving group first, then nucleophilic attack. Alternatively, these 2 steps can happen at the same time. So here the carbon is still an electrophile because it's attached to an electronegative halogen halide atom, and so that halogen will leave at the same time that the nucleophile is attacking. This is going to be what we're going to call later SN2. So SN2 here, what it's going to stand for is nucleophilic. The N is nucleophilic, the S is substitution, and the 2 does not mean that it's 2 steps. It means that it takes both reactants, 2 reactants, for it to happen. Both reactants have to be involved in one-step mechanism. Nucleophile attacks at the same time the leaves. So if we were writing a rate law for this reaction, how would we write the rate law for it? Well, this is going to depend on both of the reactants. We have two reactants here. One is the nucleophile, and then the other one is the what I'll call the substrate here. And so this is a bimolecular reaction. It requires both. Its rate is dependent on two reactants, and that's why it's called 2. The 2 stands for the bimolecular reaction. It depends on two reactants and their concentrations. When it comes to stereochemistry, stereochemistry is going to be affected by the way in which the reaction happens. So here we have a situation in which we can see that the bromine here was not directly replaced with this thiosulfide, or not thiosulfide, this SH minus atom, hydrosulfide. There. When the leaving group leaves here, it's not replaced in the same spot with the hydrosulfide. Instead, in this mechanism that's shown, or this reaction that's shown, the hydrosulfide actually takes on the opposite stereoisomeric configuration here, and the configuration goes from S to R product. And so we're going to see later that in the SN2 mechanism, as we can see here, the SN2 mechanism involves the attack of the nucleophile while the leaving group is leaving. So it has to attack from the back side of the molecule while leaving the space for the leaving group to leave. And so that's going to result in a flipping of the stereoisomerism here from S to R. The nucleophile attacks from the back side. The electron density repels the attacking nucleophile from the front side. From a molecular orbital theory perspective, the front side attack contains a node, and so a bond cannot be formed there. The back side is open to attack, and that's what will occur. So you can't have orbital overlap occur with the front side attack because there's a node on the front side of the lowest unoccupied molecular orbital. So that's the molecular orbital perspective. In terms of a transition state, so as we can see in this reaction, the transition state is one that's going to be approximately halfway in between. So in this transition state, the bromine will be in the process of leaving, but the hydrosulfide will be in the process of attaching itself. And this stereoisomeric configuration will be flipping. So in the middle, actually, it will be completely flat. So we'll have this flat situation here, which is hard to draw in 3D. But there'll be a methyl group, there'll be a hydrogen group, there'll be an ethyl group, and it will be flat. And then the bromine will be starting to leave. So we draw a dashed line here to indicate that the bromine is starting to leave. And the hydrosulfide is starting to create a bond here. And so the transition state would look like this. And of course, when we're drawing a transition states, we put them in brackets and put this double cross here, which represents the transition state. And this is halfway between where the reactants are, with the bromine being on one side here and the methyl and ethyl facing left here. And then when the hydrosulfide takes its place, now the methyl and ethyl are on the right. It's the opposite enantiomeric configuration. This is right in between, while these two are kind of flipping, and it flips like an umbrella, like the groups are pointing that way at first, and then when it flips, they're pointing the other. This is transition state is right in between. Now, in terms of which reactions will undergo an SN2, the SN2 will be most reactive if it has space for the nucleophile to go and attack in the back. So the most reactive will be the least reactive. Let's start with the least reactive. Will be tertiary alkyl halides, because when the nucleophile tries to come in here and attack this carbon, it's got other groups in the way that are blocking its approach, and that reduces the speed of the reaction. It's hard for the molecules to get in the proper orientation that they can actually collide in the correct way, make the reaction happen. With secondary alkyl halides, there's less blocking, so there's more chance that the nucleophile will make it to the carbon in the middle. And of course, if you have a methyl methyl halide, these hydrogens take up hardly any space at all. So this carbon ends up being very free and open to a backside attack by the nucleophile. So here's an indication of the relative rates for methyl alkyl halides, primary, secondary, and tertiary. So in terms of SN2 reaction rates, tertiary alkyl halides hardly undergo them. Secondary alkyl halides are very slow as well. Primary is reasonably fast, and methyl halides go much, much faster. And so you can see here these numbers indicating the rate. Even if there's a lot of crowding on the beta carbon, that can really decrease the rate as well. So if you have here, this is all of these are primary alkyl halides. They are all attached to the alpha carbon that's attached to one of the carbon, but the beta carbon may have lots of bulky substituents as well that can block the attack of the nucleophile and slow down the rate. So let's look at an energy diagram that tries to describe this. So in order for this reaction to occur, we have to get to this transition state in which the bromine here, in this case being the leaving group, is beginning to leave, and the cyanide here, which is the nucleophile in this case attacking, is beginning to form a bond with the carbon. And we have that right here. The bromine carbon bond is partially broken. The carbon bond cyanide here is partially formed. To get to this transition state, you have to reach the activation energy. The larger and the bulkier the substituents here, the larger activation energy that you have to achieve, and so the slower the reaction goes. And so that is why methyl halides will react the fastest. The more substituted the carbon is. Go. So here is a comparison. If you have a methyl alkyl halide, well, reaching the activation energy is pretty easy. There's not a lot of stuff blocking the nucleophile, so the nucleophile can get in there pretty easy without too many problems. However, in this case, we have some steric hindrance here due to the carbon. And so this nucleophile is going to have to approach with a little bit more energy to overcome the repulsion to this group here, and in a better orientation to make it. And so the activation energy here is going to be larger. And for a secondary alkyl halide, the activation energy is larger. And for tertiary substrates, an SN2 reaction can't really. So what if we had neopentyl bromide here? Neopentyl bromide. And neopentyl bromide would be this bromine, and then we have a one space here, and we have this guy here. So the alpha carbon's primary, but the beta carbon is highly substituted. And so the neopentyl halide will undergo a very slow reaction. Even though it's primary, this neopentyl group here is going to block off approach by the nucleophile quite a lot. And so it would react quite slowly, even though it's primary. So let's think about what makes a good nucleophile. So we need a strong nucleophile for an SN2 reaction to occur. So the question is, what makes a strong nucleophile? Well, in the case of hydroxide here, it's a strong nucleophile. A strong nucleophile will be one that has a very dense negative charge to it. So here we got this hydroxide, very dense negative charge. It's small. It's on a small oxygen atom. That oxygen atom really it's quite negative. It's going to be very attracted to the positive carbon here, and will initiate this reaction quite readily. Water is a weak nucleophile. It's not negative. It doesn't have a negative charge. It's not nearly as attracted to this partially positive carbon. Also, the structure that you get in the end, you'll notice this is a nice and stable structure, no formal charges. But when you have a neutral nucleophile like water attack, you end up with a positive form. you end up with a less stable product as well. And so you can imagine too that the activation energy is larger because you'll have to get up to a higher energy to get to this unstable product here. And so strong nucleophiles will one obvious way to recognize a strong nucleophile is it's going to be negative. Weak nucleophiles are not negative. When it comes to strong nucleophiles, we also want them to not have too tight of a grip on their electrons. We want those electrons to be able to be donated, right? So strong nucleophiles, the strongest of the nucleophiles here are going to be on the left. They have a negative charge, but that negative charge isn't too tightly bound on the iodine, so it can be given away to make a bond here. And then sulfur here has a little bit weaker of a grip than the oxygen here. So we have a small tight negative charge, but also that negative charge here is easily given up, right? It's not held on to as strongly with the sulfur atom as the oxygen. And then with the carbon atom, it's held quite strongly because of basically the nitrogen atom here and the fact that it's involved in this triple bond. But it's still a strong nucleophile. Notice the strong nucleophiles are all negative. Weak nucleophiles are generally those that have an oxygen atom and are neutral. Water, alcohol are weak nucleophiles. So you do need to be able to identify what's a strong nucleophile, what's a weak nucleophile. The key idea here when I'm talking about the size of the atoms is how polarizable the atoms are. So the weaker the grip on the electron, the more polarizable the atoms are, meaning that electron density can kind of move left and right or up and down, around, side to side, instead of being so tightly gripped. So if we have oxygen, that negative charge is very, very tightly gripped. Or if we have a fluoride ion, it's very, very tightly gripped. They're not very polarizable, even though they're negative. In iodine, that atom is very large, and so that negative charge is not very tightly gripped. In addition, we'll later have to think about the solvent, which we'll come up to a little bit later. So one complication, as we said, is some of our strong nucleophiles, like OH here, or RO minus. These are pretty strong bases. And so when you have a strong nucleophile, it's also a strong base, you may not get substitution. You may, in fact, instead get elimination. So if we have a strong base here, we can have an elimination. In that elimination, a hydrogen atom is removed and the halogen atom. And so now these carbons have 3 bonds. And to make a 4th bond, ultimately, a double bond is formed between carbons. And at that point, each carbon has 4 bonds. And so in terms of elimination reactions can also occur in a concerted fashion. When they do, we call those E2 reactions. Again, 2 here meaning secondary, meaning that the reagent and the substrate here will both be involved in the important reactive step here. So in this case, we see a base. That base is undergoing a proton transfer. So remember proton transfer style, we learned that in chapter 3. We used it again in chapter 6. This involves the transfer of a proton, so the H plus ion. So the base here uses its 2 electrons to donate to the hydrogen and make a bond. When the hydrogen leaves, it does not take any electrons with it. It leaves them behind, which is the second arrow here. Finally, in order to make a double bond here, we can't have a carbon with 5 bonds, so simultaneously the leaving group that leaves as iodine. So we get the result is alkene, a carbon-carbon double bond, and we also have the conjugate acid of the base and the halide leaving. So E2 elimination is conservative. The base removes a proton in the beta position, and then we have the loss of the leaving group that occurs at the same time. E means eliminations. 2 means bimolecular or secondary. It means that when you write the rate equation, the rate equals the K times the concentration of each of the reactants. And in this case, the base and the alkyl halide are both involved in this one-step mechanism. So they are both reactants here. And so this is bimolecular, involving both of the reactants. Rate determining step. Now, as we were talking about before, hydroxide is both a strong nucleophile and a strong base, and that presents issues for us because a substitution SN2 or an E2, either of those can occur. Um, so, especially in the case of a tertiary alkyl halide, remember that for the tertiary alkyl halide, the SN2 reaction is extremely slow. So it's not going to happen very quickly at all. The tertiary substrate is too sterically hindered. The nucleophile cannot approach from the backside. However, if we have a hydrogen, it is sticking out from these groups. So the hydrogens are all here on the edges. So those beta hydrogens are quite easy to remove. So we can see how having a tertiary substrate really influences this reaction to become more an elimination reaction and not a substitution reaction. So the substrate will really affect whether a elimination or a reaction, substitution occur. So now we have two factors we're considering. We're considering whether the nucleophile is a strong base as well, and we're also considering whether the substrate is primary, tertiary, secondary, primary, secondary, tertiary. When it comes to which product will be produced, sometimes there are multiple stereoisomeric products that can be produced from an elimination. In this case, we can see, let's say we're doing an elimination, which will produce a double bond here. That double bond could ultimately be trans or be cis, but cis double bonds have a steric strain. And so the thermodynamically favorable product will be the trans isomer. And so that's one thing to consider when an elimination is occurring, is that the more thermodynamically stable product will be the trans one. However, depending on the conditions of the reaction, going into a trans configuration may or may not be possible. Let's talk about the details of that. We will in a moment. So again, like we did in the past when we were comparing the stabilities of two structures that are simply stereoisomers of one another, one way we can do that is by combusting them and see how much energy comes out. The more energy that comes out, the less stable that the initial reactant was, and so we can see that the cis-2 butene is about 4 kilojoules per mole less stable than the trans-2 butene. Not by a huge amount, but it is slightly more stable due to the steric hindrance of the methyl group. Difference. The combustion energy is 4 kilojoules per mole, the cis isomer being 4 kilojoules per mole less stable trans isomer. In terms of the alkyl groups, in terms of substitution, so this is something we've learned in a previous chapter too. The more substituted double bonds are those that are most stable. So the more substituted the double bond is, the more stable this is due to the hyperconjugation that we discussed previously. This is due to the fact that there are unhybridized p orbitals here, and there are hydrogen atoms attached to carbon over here. So those hydrogen atoms can pop back and forth. There's a little bit. It's not quite resonance. They're not actually moving, but there's that kind of force of motion that they could hydrogen atoms could pop over to the p orbital, and you can change the hybridization much more easily. That was referred to as hyperconjugation, chapter 4. So more substituted double bonds here with more carbons attached to the carbons in the double bond are more stable. When it comes to ringed alkene, we talked about this previously in chapter 4 with alkanes, but it's also true with alkenes. In terms of cyclic alkenes, only the cis isomers will be stable. The reason why is because the only way for this to go into a ring is for these to be cis. If it were trans and this methyl were out here, you'd get a very ugly type of ring formation. It wouldn't be able to make great. There would be angle strain. The angles would be bad. The bonds would be longer than they want to be. So in a ring, we don't have to say cis or trans in terms of the alkene, because we already know they're going for these bicycloalkanes, or bicycloalkenes rather, since these have a double bond. Those in which the alkene will be in a cis conformation. This increases the stability of the molecule, whereas if only a trans configuration is possible, there's less stability there. And so this is referred to as Brett's rule. So here we end up with this kind of trans type of configuration. You can tell by looking at it that the angles would not be great. The angles here are much more favorable at about 120 degrees for a carbon-carbon double. So now it's time to talk about which type of product we will have, because when we have an elimination, often there's more than one product that we get from the elimination. So for example, here we have two potential products in the reaction. Why is that? Well, because if we look at this, we have two positions for beta hydrogens. We have two hydrogens here, and we have beta positions here as well. And so if we have our base coming in, which in this case our base is the ethoxide ion, which is often abbreviated OET. You're going to see this more and more often. The ET meaning ethyl. So this is the same as this oxide, negative charge here. So when it comes to this reaction, if we're doing an E2, remember that there's a proton transfer that is involved. So these electrons here make a bond with the hydrogen. It leaves its electrons behind, and then the leaving group leaves at the same. But alternatively, we could also have the situation where we have the ethoxide do the proton transfer on this beta here. So we here make a bond to the hydrogen leaving its lone pair behind, and then the bromide group simultaneously. So if we go through the red mechanism here, we're going to have the double bond here. So the result here, this is the red result right here, would be what's called the Hofmann product. What you'll notice about the Hofmann product is that it's only di-substituted. There are no carbons attached to this carbon on the double, only to this one on the right, two of them. However, if we go via the blue mechanism, we'll end up with the Zaitsev product. And so the result here would be that we have a double bond at this position, which is tri-substituted. So we can see that due to the greater stability of the more substituted double bond here, we get a preference here for the so-called Zaitsev product, where the double bond is positioned between the second and the third carbon, rather than the Hofmann product, where the double bond is between the first and second carbon. And so this is referred to as regioselectivity. Say regio, you can think of region. What region of the molecule will this reaction occur in? It will be preferred in this region rather than this region here. So here we have, when we have various constitutional isomers, these are constitutional isomers of one another, not stereoisomers, double bonds in a different place here. When we have multiple potential constitutional isomers that can be formed, and one of them is major and one of them is minor, we refer to this as regioselectivity. And depending on the base that we use, and the other factors here that are involved, we can control the regioselectivity of the. So in terms of bases, ethoxide ends up being a kind of small base compared to these other ones here that have lots of carbons attached. So we refer to these two down here, the tert butoxide here and this very sterically hindered alkoxide ion. We refer to these as sterically hindered bases, whereas the ethoxide or methoxide or hydroxide, so we can include in group here, we can also methoxide, hydroxide would fit into the non-sterically bases. And so one thing that we see is that when we have a non-sterically hindered base like the last one we saw, we get a preference for the Zaitsev product versus the Hofmann. However, if we have a sterically hindered base, we end up with the Hofmann product rather than the Zaitsev, because what's driving this here is thermodynamics. So thermodynamics meaning here, these are producing the Zaitsev more thermodynamically stable product. However, when the base is sterically hindered, it can be harder for it to get into a position to grab the protons here. Whereas the protons that were on this carbon are way out here, it's easier for the sterically hindered base to get to them. And so these end up being determined by kinetics rather than thermodynamics. It's just faster for you to get to the product. Whereas for the thermodynamically favorable product, you'll get that if it's easy enough for the base to get in there and write proton. So that just answered that question. Sterically hindered base will prefer the Hofmann product because it can more easily get to the protons that it needs to get to when it's products, and the reaction occurs more quickly. So these are three sterically hindered bases that can be used. These are often sometimes called non-nucleophilic bases. So some examples are amines as well, so not just tert butoxide. Tert butoxide, of course, would be a strong base and a strong nucleophile, whereas here these would be pretty strong bases as well, not as strong also. So let's talk about which product we have here. So here, this has ethoxide in it, which is a non-sterically, and so we would get the so-called Hofmann products. So our two potential products here would be so one of them would be where we have a double bond right here. That would be the Zaitsev, and that would be from removing this hydrogen right here and this chlorine. So we'd make a bond right here. Whereas the other potential product, the Hofmann product, would be if we make a double bond right here. And in this case, it would be this. So in this case, it would be this one, this hydrogen here, rather than this hydrogen. And those are our two possible products. Here, it would be the Zaitsev product that is preferred. It's more substituted. So the less sterically hindered base will be more substituted product. And so again here, when it comes to this reaction, we can either have a double bond on one of these methyls with this hydrogen here removed, or we can have a double bond here with this hydrogen. And in this case, we have hydroxide, which again is not sterically hindered. So we're going to get the more substituted product. The double bond will be right there. So that's this double bond here, and then we have the rest of the molecule. This is these two methyls are right here on the left. Double bond is here. With tert butoxide, however, it's sterically hindered, and so it's going to be easier for it to get to this hydrogen right here. Notice that this hydrogen is going to be kind of blocked off by the things around it. This one's hanging out way out here, easy to get to. And so this one will make a double bond in the less sterically hindered position. However, it's less thermodynamically stable, right? But it's more kinetically favorable because base comes in to get the hydrogen. Easier for it to get in here than it was partially blocked on the approach by all these groups. So in terms of stereoselectivity here, so besides regioselectivity, there's also stereoselectivity. So remember, regioselectivity was telling us about basically which constitutional isomer we would get. Where would the double bond be? So in this case, the double bond is in the same spot in both of these products. It's on the starting on the second carbon. The difference is that in the products of this reaction have two possible isomers. stereoisomer, the trans isomer or the cis isomer. And we already determined that the trans isomer is more thermodynamically favorable. It also turns out that the production of the trans isomer is also more kinetically favorable. So remember, when we're thinking about kinetics, we're thinking about this space right here. So here, the activation energy here is less than the activation energy of the cis product. In addition, the trans product is more thermodynamically favorable, having a lesser draw a line. This is the delta G here. Remember that the delta G is what tells us what's thermodynamically favorable, and the activation energy tells us what's kinetically favorable. In this case, the trans isomer is both thermodynamically and kinetically favored. So we're going to get a much greater amount of this major product than minor product. And this is referred to as stereoselectivity. So not where the position of the double bond is, but the whether we'll have cis or trans stereoisomer at the end. Finally, when it comes to E2, a lot of the times there's only going to be one possible isomer that can occur. This is due to what is called stereospecificity. Now, stereospecificity takes a little bit of time to explain, so we're going to finish up talking about the E2 mechanism, stereospecificity, in the next